OK. Donc, bonjour tout le monde. Bienvenue au séminaire de l'Institut quantique de cette semaine. J'espère qu'il ne fait pas trop chaud chez vous. Vous voyez, chez moi, il fait quand même pas mal chaud, là, donc mon background. Mais donc, aujourd'hui, on a la chance d'avoir Simon qui va nous présenter une présentation sur des réseaux de neurones. Puis je vais aller en anglais pour la suite. Donc, welcome everyone. So, please close your microphones unless asked otherwise for this talk. But this time you're welcome to open your camera feed. So we're trying to make this a little bit more interactive this time. So hopefully this will work. If you have any questions during the talk, please raise your hand or lever la main option. Simon and I will moderate the discussion and ask you to open your microphones to ask a question. So that's it for me. Have a good talk, everyone. And thank you, Simon. Go ahead.
Thank you, Cal. Okay, so hi, everyone. Thank you for coming. I actually only see my screen, so I don't see who's there, and I don't see if you raise your hand or not. So it will be Cal that will tell us. And yeah, so we can go right away. So my presentation is supported, we could say, by a lot of people in the sense that I didn't do much of the work myself. The work is mainly coming from Chloé Aminata in André Marie's group in Sherbrooke, and two of her interns did the heavy lifting on this one, which are Marc-Antoine Gauthier and Benjamin Gloro-Paré. At Mila, where I work half-time, Umar, which some of you know because he was in Sherbrooke previously, Umar did a lot of work on this. And mainly everything that I will present today was discussed extensively with Umar and understood better probably by Umar than myself. So if there are hard questions, maybe, I don't know if Umar is there, but maybe he will be able to help me today. Otherwise, at Mila, I also talk often with Simon Blackburn. And of course, Yoshua Benjo is the instigator of the idea of learning, of using deep neural networks to learn materials properties. So some of the credits goes to him, but he's very busy, so I don't talk to him that much about these projects, unfortunately. So in science, we have access to something which could probably rightfully be classified as some kind of a spiritual experience, and hear me out. So when you study a physical problem long enough, you might develop very deep intuitions about the given problem. So I'm not only talking about like intuitions of theories that you read in books, but especially intuitions about unsolved physical mysteries. Because in those cases, you need like many months, maybe many years to make the problem accessible and put the problem in your mind. And you do so without ever reaching a clearly defined like recipe of rational steps or mathematical steps towards the solution. So when you're navigating such problem without a rational solution, it's your intuitions that gets pushed to their limits. And there are tales, for example, with Einstein, that your mind can become capable of predicting the solution directly from your intuitions. And not the whole mathematical solutions, but I mean like key ideas in the problem. So there are famous thought experiments that have been discussed for this. And this is without knowing all the details. These intuitions can be your guide, and very often you can like actually do experiments in your mind in the sense that you can predict what nature will produce as an experimental result to guide the decisions you make while you're trying to find a solution. Now, I think that experiencing such intuitions is more important to scientists than we'd like to admit. It's the only time, in some sense, that the complexity of reality is completely captured in your mind. Without you being completely conscious of it, you're so in tune with the problem that you really get to know nature at that point. And although we like to say to our funding agencies that yeah, we do this because in 50 years or 60 years, what we do might be useful. I think many of us really do it because of this experience, because at some point you get very close to the physical laws when you work in a problem long enough. So I know I talked about the spiritual experience, but this is all I wanted to say about this. My point is mainly in this, that intuition plays an important role in how we do science. And the main idea I want to discuss in this talk is how we could use some kind of what I call machine intuition, which would be embodied in that case in neural networks, to help us like circumventing the conventional way of computing useful properties of materials, which is usually done with theories like the density functional theory, for example, and can take many seconds or a lot of time to get the properties. Maybe we could do the same thing with neural networks without understanding everything that's going on inside the neural networks, but get the properties a lot faster. So in my talk, I will break things down in three big parts. First, we will discuss a little bit the neural networks and how we can see this as being the intuition of machines. Then we will go to how you can break materials down to numbers in order to put them into algorithms like neural networks. And then I will discuss specifically how neural networks were designed in the latest years to address the problem of predicting the properties of materials. So, neural networks as a machine intuition. Well, first of all, simply consider on which problems neural networks have revolutionized things in the last decade. We have visual recognition tasks, speech recognition tasks, speech synthesis, machine translation, games, databases. Actually, databases is a little bit more specific, but take those first five. These are all tasks that we know are solvable because our brain do it, like recognizing someone at a glimpse. Your brain can do it, so probably there is an algorithm that can do it. However, when we try to like put every steps of this probable algorithm in a computer and try to handcraft every step of the algorithm, we couldn't get the computer to do it. It was computers were very poor at visual recognition. Same thing goes for speech recognition, speech synthesis. Like those are things that your brain do intuitively, and those are very, very difficult tasks if you want to break down like every steps of the algorithm. So, Andrej Karpathy, which is head of, I think he's head of OpenAI right now, wrote something in 2017 which is very interesting and goes a little bit like this. And the picture that I'm showing here comes from a talk by Lei Wan, which is a physicist working with the neural networks, which is in advance in that field right now. So, Andrej Karpathy talks of software 2.0 in the sense that usually when you write software, you want some input to produce some output, and the task that the programmer have to do is to write a program that will be used in the computer to produce the desired output. In software 2.0, and this is a little bit what we do with neural networks and machine learning in general, you take the input that you desire, and if you have enough outputs, like these examples of desired outputs, you can ask the computer to come up with a program. And by a program, I mean specifically like a sequence of mathematical operations, which is exactly what we try to input in the computer when we write code. So the idea in that case would be that instead of giving a single program of the whole program space, you would give to the computer a space, like a subspace of all possible programs that are accessible to the computer. And given enough examples, the computer will, like, with a given optimization algorithm, could move in that space. And if you know a little bit about where I'm going with neural networks, you probably heard about stochastic gradient descent. And in that case, it makes sense that one of the efficient optimization algorithm for that kind of task is to add some randomness in the process where you search for the best possible program. Now, this has some interesting consequences in the sense that you probably won't end up always at the same program. And in that case, the program that you will get won't be deterministic. It won't give you the same answer for any run of the training of the program. But nevertheless, you might get a lot better results, because if you allow for the program to become a lot more complicated than what you could possibly have written down by yourself, then you might get a lot better results for the task that we mentioned before. So usually those programs are neural networks, as I said, and they are optimized by gradient descent, just by finding for every example like how you can improve the program for that example and nudging the program a little bit in that direction. Now, a neural network can be seen as a program in the sense that it is a sequence of operations, okay? And that sequence of operations adds up to a single function. And that function will have many free parameters, because if we want this space for all programs covered by the neural network to be as big as possible, we will need a lot of parameters, typically several millions. So starting with that function, which is very free, we will be able to get something interesting. Now, typically, the neural networks are presented as follows. So you have first, you take your input x inside the first step of the program, or the first step of the function. And this first step is simply multiply by a matrix, add a bias, and those W's and B's are learnable or are adjustable parameters. And then you get something called a pre-activation. And then you pass this pre-activation inside what we call an activation function, which is historically presented as being the sigmoid function, which is this function. But recently it has become obvious that the ReLU function, which is just if greater than 0, take the value, works a lot better, very often. So you have matrix multiplications and simple if statements. So those are very simple operations from a computing standpoint. And then you do that again for another layer of the neural network. And then you do that again, and you get the result of the functions. So the usual way to represent neural networks in papers, for example, is not that large mesh of operations, but rather simply this layer of operations directly drawn like this. So linear ReLU. This is matrix multiplication if statement, matrix multiplication if statement, and so on. So you can see that it kind of forms a program. Now, once we have the result, we want to optimize all the free parameters that we let in the program. So we will have to define an objective, which is called the loss function, and this objective will be optimized. And to optimize the objective, we will want to optimize it for any possible input and output pairs or data pairs that the program might encounter, okay? Not the data pairs that we have stored in our database, but which the program could encounter. Now, the ones that we have in our database are examples or a sample of the actual distribution you might find in nature. So that's why there's an expectation, like the very abstract statistical expectation here. In practice, we take all the examples that we have and we sum over them. Okay, so this is the complete loss function for your training data. But it's not the actual objective you want to minimize. So keep that in mind. What you want to minimize is the hypothetical, like if you had all possible examples in the world. So the way to do that is simply to follow which path or which small variations in those parameters could give you an improvement over this loss. So you could simply compute the gradient of this loss. And since the gradient can exchange with the sum, you can compute the gradient example by example. And then you get a mean to update everything. The gradient is taken as a function of theta, and I remind you that theta stands for all free parameters in the neural network, or all free parameters in the program. So once you know the gradient for theta, you can update all of those theta separately, and it should give a better program. This is called stochastic gradient descent because we don't do it for the whole expectation value, and we don't even do it for the whole data set that we have. We do it for subsamples. This adds randomness to the process, which guarantees that you won't get stuck in very shallow local minimas, and it allows the program to move around, but it also makes the program not deterministic. You won't always get the same thing. you would get a very good program nevertheless. So there are many advantages of working like this. First of all, these are matrix multiplications and if statement at a very low level. Sometimes you can include more complicated computations, but it means that it is computationally homogeneous. It's very like the operations are always the same. It is very simple to bake that into silicon, and that's why like GPUs are used in that case, because those are simple operations that can be like made very optimized in our hardware. It will a neural network of a given size will always take the same time, so there's no problem of like it may do more iterations or less iterations. Once the training is done and you have a neural network, it runs very quickly and it gives you an estimate. It uses constant memory for the same reason. It is highly portable because, again, matrix multiplications and if statements are easy to do on any hardware. The performance is flexible in the sense that if you take a neural network twice as large, you would get twice as much running time for the neural network, roughly speaking. And it is very modular, and this one is pretty important. But before to go, I will illustrate what I mean by modular. Before to go there, notice that this is a lot analogous to like machine intuition, as is the point I'm trying to make. In the sense that intuition is always like instantaneous. You don't have to think about it. There's no work to do. The energy consumption of your brain on an intuitive operation is standard. So there is something very like clean about having this kind of capability in our computers now. And what I mean by it is very modular, I mean that this sequence of operation can be split anywhere. So you could, for example, say, okay, I want to stop here, get an intermediate state H, and start with another input, or maybe the next input in a series, and add this to the intermediate state. Maybe you can have an operation like addition to compose that one, or concatenation of the vector, and then you get a new vector, and you pass that to a new function. So all of those blocks would be separate functions with a separate set of parameters, but overall, you can build like many programs with this. Okay, and yeah, and as a spoiler alert, at the end of the talk, I will show you this model, which is very big. I will not like go in every detail, but I want you to understand like various parts of the models that are used. This is a very big model that is used to predict the properties of molecules, for example. And you can see that they are like linear operations, as we saw, sigma time operation W. But then there are matrix multiplications, element-wise multiplications, sums, and all kind of other operations. This is a very big neural network, and it gives you a flavor of how bad things can get. Now, there are disadvantages to using these kind of tools. For example, it requires a lot of good quality data. The results, as I said, are difficult to reproduce exactly. I was speaking with someone at Mila recently, and he explained that even in the case of like the same random seed on very similar hardware, they had a difference of about 1% in classification performance for a given model, because the GPU they used in one case was not exactly the same as the other GPUs, and the precision in the float operation was slightly off, and because of that, like the accumulation of all these operations in the neural network caused substantial differences in their results. So it is a tool that will give you approximate solutions, but for many problems, this would be sufficient. Then a very big problem with the neural networks is that they fail silently. And what I mean by that is that you write a code for a neural network, and sometimes you plug things in the wrong way, and you won't know about it because like those are simple operations and they might still work, but they might not do exactly what you intended them to do. And then you would get, for example, a 95% performance on a fit, and you could have got a 99% if you had plugged things the right way. So this is they fail silently. Then then yes, another very big problem is that if there are biases in your training data compared to the task that you're trying to do, for example, if you're trying to recognize faces and in your data set there are only white people, then you might have a hard time classifying the faces or identifying people of color. And because of that, this is a very embarrassing failure, because then your program is biased the same way that your data is biased. And we know that in our world, there are a lot of biased data for very sensitive issues. So yeah, there's a lot of research done in Montreal about this. So this is it for neural networks as machine intuition. I will take a sip of water. Cal, are there any comments or questions at this time?
There are no raised hands, so no questions, it seems.
Okay, so I will ask something at the audience. Please, right now, please raise your hand if you want me to continue. Cal, can you tell me a fraction of how many people have their hand raised?
Okay, so everyone has their hands raised, so I think it's okay.
Okay, that's good. Okay, so we go one step further into the rabbit hole. So the task we are considering in this talk for making those intuitive programs, which are the neural networks, is to predict the properties of specifically crystalline materials. Okay, this is a task that we undertook with Umar and Chloé and André-Marie some time ago. So there are already similar tasks, as I said, with density functional theory, which is a quantum mechanics theory that Thomas presented very well last week, if you were there. So I won't get into the details about this, but remind simply this. In this theory, you need the atomic positions of every atom in your material, the atomic number for every atom, just to know what atom it is that is there, and then the lattice vectors. So you have to know, if it's the crystal, you don't want the positions of all the atoms because there are too many. But if you know the unit cell and you know the lattice vector or a super lattice, just to catch some longer length properties, then you use those. And then ideally you need the symmetry group, because it encodes how the lattice is structured. So from there, DFT can give you many things. For example, the formation energy of the material, the band gap of the material, magnetization, if you add some consideration about the spin in there, elasticity, bulk moduli, and so on. So you can get many properties. With other methods such as DMFT, which we do in Sherbrooke, you could get other things. And there are many possible algorithms derived from those very sophisticated tools can give you almost anything you want. But basically, you always need only a few input values to get everything. So ideally, if we want to build a neural network that could give you the results or an approximative result for those things in seconds instead of hours, you would take the same inputs to do the work. Now, what you will need to do that also is a lot of data. So there are a few standard data sets that are used in the literature. Maybe I will mention some of them. So the Inorganic Crystal Structure Database, ICSD, this one requires paid access, and it contains 218,000 structures gathered since 1930. Those are all experimental structures. So this is experimental data. But because of that, there are not so many properties which are over all the data sets. So you don't have the magnetization for those 2,000 samples, so you cannot try to predict that. But this will give a good data set to scan at the end with your algorithm to see if you can find some interesting materials. Then there is the Materials Project database, 120,000 structure, they claim. Actually, if you look, then you can have the formation energies, band gaps, magnetizations, and some other, which I forgot to fill here. and 52,000 band structures within those materials. And actually, once you've like purged a little bit and played around with the materials, you realize that there are around 50,000 usable materials for a machine learning setup. Then there's the Open Quantum Material Database. They claim to have 600,000 structures, so this is a lot more than the two others. You can get the formation energies and the band gaps for those. And in their paper, there's an interesting statement, is that the mean absolute error between experimental measurements for a subset of materials and their calculations, and by these calculations, they mean their DFT calculations, was to be 0.09. Okay, so I have to go back a little bit. I said these are experimental, the ICSD database are all experimental data. The materials project is synthetic data, so this is data computed from density functional theory. And the Open Quantum Material Database is also synthetic data computed from density functional theory. So the mean absolute error between experimental measurements and their calculation, this gives like a rough estimate of how precise DFT is. Okay, so 0.1 electron volt per atom. So because DFT is precise that much, if we train a neural network on DFT data and we get in that range, it will be like very satisfactory. And then the deviation between different experimental measurements in the data that they used was around the same range. So even like if we could go more precise than this on our fit, it might not be useful because the experimental data within error bars will give you almost the same uncertainty. So getting to 0.1 EV per atom would be very good.
I would have a question, Simon.
Yes.
Just if you go back to the previous slide, so you say that this is all synthetic data, but they compared it with experiments. So which database did they use to compare? I mean, was it the OCSD or?
Yeah, good question. I think when I say they compared it, they compared it to, for example, maybe 1,000 or 2,000 experimental points, and 1,000 or 2,000 data would not be enough to train a neural network properly. Yes. Yeah. Okay, so since it wouldn't be enough data, I didn't consider and I didn't look at what actual data set they were using.
Okay, thanks.
Good. Okay, so we can now craft a reasonable plan to a big project trying to predict the properties of materials with neural networks. So first, you could take OQMD and MP, like the Open Quantum Material Database and Materials Project dataset, and try to predict their DFT energies and DFT band gaps, just to see which one of the neural networks does the best at these kind of tasks. Okay, and actually there's something interesting with the neural networks. When I showed that it was modular, it means that you can train on hundreds of thousands of data points from DFT, like the whole neural network, and then you could fix the first parts of the neural networks and only use the last part to fit smaller data sets. So this is called transfer learning, and that's why I write you can train and pre-train on OQMD and MP energies and band gaps to discriminate models. Whoops. Then the second step would be, once the best models are established, those providing the best representations, and by representations, I mean that intermediate state within the whole neural networks. Like once you get a very good representations, this representation might be useful for other tasks. Like you could do only a linear fit on that representation and get very good results because it encodes or it embeds the complexity of materials. So when you get the best possible representations by screening those data sets, then you can retrain on reduced data sets of a given useful property. For example, the superconducting critical temperature, and that you might get very good results. So, and at the end of the day, if you have a neural network that is trained like this to predict TC, then you could screen like the whole ICSD database or the whole materials of OQMD for promising candidates for that specific properties for which you didn't have a lot of data. And then you could submit those candidates, those promising candidates, to DFT calculations just to confirm that they give something interesting, or to DMFT or any other methods, and then submit the most promising candidates among those to like as candidates for actual experiments if they are synthesizable and so on. So this is like the roadmap for most of the projects we see in the literature on predicting properties and suggesting new materials from neural networks. There are actually alternatives to this. You can try to generate new materials from scratch, but this is a very advanced topic, and I'm not very familiar with those methods, and I haven't tried them myself, so maybe it's better that I let someone else discuss this at some point in the future. So there are also problems within the database that I mentioned. So for example, in the materials project database, there is this distribution of monoclinic, of like the crystal systems that you can find in natures. And so the question at that point is this representative of the actual like distribution you might encounter in nature? Is this representative of the distribution of the actually interesting materials that you might want to screen at the end? So this might be a problem, because if your neural network becomes very good at classifying or at giving the properties, the critical temperature of an orthorhombic crystals, for example, but very bad at trigonal, and it turns out that all you want to do is trigonal or triclinic, then yeah, your neural network didn't have the right data to train on. We have also witnessed another problem on the formation energy. For example, the formation energy contains like a very odd distribution. And when you look into it, you find that it's because within materials project, there are materials that were computed with the Hubbard U, and some materials were computed without the Hubbard U, and this is why you see two humps. So there are actually two distributions in there. So at that point, you could say, okay, if I want to fit the formation energy, should I like split the data set and have a data set with U and a data set without U, or take the whole data set? And unfortunately, in the past, people have already like made claims about the quality of their model on that measure of formation energy per atoms. And it's not always clear in the papers if they had this consideration in mind. So maybe a good part of their model is good at fitting if the original material was using U or not. So this is it for like breaking down materials to numbers. Okay, so we have the idea of using neural networks as machine intuitions to predict material properties. Then we have the data sets and the data that we will need to use, and I've outlined some of the problems that we have with that data. But nevertheless, now we could talk about like, okay, but what kind of neural networks would be good for materials? So again, Carl, I will ask if there are any comments or questions about that part, and then I will ask people to raise their hands, but after. So first, questions.
So there doesn't seem to be any right now.
Okay, and so again, like before, if you are ready to go further, can you please raise your hand, and Carl will tell me if it's good.
Looks good. A lot of people are putting their hands up.
Okay, so because otherwise we can stop. But okay, let's go into the neural networks, and I have. Okay, that's good. I have 25 minutes left. No, it ends at, okay, in 10 minutes. So let's try to do that fast. Okay, so as I said, when you break down materials into numbers, you want maybe the atomic positions, the atomic numbers, maybe the lattice vectors, and the symmetry group. Unfortunately, in the literature right now, most of the models that uses neural network focus only on the atomic position and the atomic numbers. Now, this is a huge problem for crystals, and you don't have to point it out to me. I already know. Unfortunately, I didn't have the time to come up with an idea or to do something meaningful about the lattice vectors in the symmetry group, because I only wanted to know what people had done so far. But if you had very good ideas, contact me or Umar or try to start your own research group, because this is a very big problem in the field right now. So from atomic positions and atomic numbers, can we predict like everything that DFT predicts? And the reason why we only focus on those two is because of pharmaceutical chemistry or organic chemistry. These people don't care that much about crystalline structure because they only want to apply neural networks on organic molecules. And in those cases, you can see that all you need is like the graphical structure of the molecule to have a lot of information about the thing. So starting from the atomic flavor, so every atomic number in the material and the positions of every atom, something you can build is a graph. And the reason why people went to graph is obvious. It's because like Facebook, Twitter, and Google all had done tremendous work about working with graphs because of the social graph in Facebook and Twitter, and because of like the internet graph if you consider Google. And because of that, neural networks that apply well to graph data were already well studied when the interest became to use that for materials. So you start from atomic numbers and you put those atomic numbers on the nodes of a graph, and you take the atomic positions, and from the atomic positions you can like craft the edge between different atoms. So there are many ways to do that. Umar explored this avenue extensively. We don't yet know what is the best way to do it. One way is simply to take like each atom and its direct neighbors. And the algorithm to do that is a Voronoi cell splitting algorithm. So you can do that. An easier way to do that could be simply to say, okay, from a given atom, just insert a given cutoff, and every atom that is within that radial cutoff will be considered a neighbor in the graph. But yeah, constructing the graph of a given molecule or of a given crystal is a task in itself. Then there is the issue of periodic conditions, and it turns out that this is not so hard for crystals, because you simply take the unit cell and you consider that if one of the edge would go out of the unit cell, you can connect it back to the one cell. So for example, this crystalline structure gives that graph, and this crystalline structure gives that graph. So I think it is obvious that this is not the ideal starting point, but it is a starting point, and people have worked on it. So it's probably good to go see what they've done with that. And that's what I will go for the rest of the talk. However, if you have ideas about like what would be the best way to encode a graph in the computer, not a graph, a crystal structure in the computer for neural networks, feel free to bring some suggestion at the end, or think about it, because I think it's still like an open problem of that field. So if you go from this to a graph, you need to have intermediate steps. So I will present you like the building blocks of a full graph neural network algorithms for materials. And this will be in 3 parts. And the first part is the embedding. So how do you like take the atoms and their positions and put them in a graph in the concrete way? And basically the idea is as follows. For every atom, and maybe its neighbors, and there are many ways to do that, you build a vector. So on every node of your graph, there will be a vector lying there with the properties of that atom. So for example, you could choose handcrafted features. You could say, okay, so for every atom, I would have a 4-dimensional vector, and in that vector, I will input the mass, the electronegativity, the valence, and the melting point of that particular atomic properties, taking the properties from the periodic table. But this has had some success, and right now it's hard to say which is better between that or the other one. But machine learning people usually like to learn everything. So start from like the most basic thing you can and let the neural network learn as much as it can. And to do that, you can start with what they call the one-hot encoding. So every atom, for example, carbon, will be a unit vector in a 120-dimensional space. each dimension of that space being one of the elements of the periodic table. And the reason to do this is obvious. It's because you cannot say that phosphorus is larger than carbon just because its atomic number is larger than carbon, because for some other properties, for example, the electronegativity, it will be the other way around. So instead of going in a space where you would use the atomic number as an input itself, it's better to go in a space where every element is orthogonal to each other. And then when you go through the linear transformation that are in your neural network, you will like deform this representation so that some atom will become overlapping with others and some will become closer to other in this vector space and so on. So this is the idea of embeddings. So for every atoms, there will be a vector. You can also do embeddings for the edge. So for example, the distance between two atoms could be encoded in a vector lying on the edge of the graph. And then you would have like edge embeddings, state embeddings, and this name, embeddings, comes from natural language processing where people had to do that for words. So when you have words in a big book, you cannot like just use the dictionary as is. You have to create like vectors for each of those words. So once you're done with embedding, you have a graph. Every node of your graph and every edge of your graph contains a vector. So you can start from this graph and use all the vectors and do either what is called graph convolutions or message passing in the literature. And basically, it's always the same idea. You take all those vectors that compose your graph, and then your graph is completely abstracted away, and you pass those vectors through a full-fledged neural network, which is parameterized by some free parameters, and it gives you new vectors. But the important thing is that those new vectors will be of the same dimension. So they will lie at the same places in an updated graph. And now you can see that in this image, some of the locations of the atoms have merged colors, because now the information about each flavor of atoms is distributed everywhere in the graph. Now, you can do this many times, actually, to be sure that like the information from every atom goes to every other atom, and that's why they call it message passing. So you pass a message from a given individual in the graph to another individual, and so on, until like the whole graph knows about everything. So this is like the message passing or graph convolution step. And at the very end, one of the very big problems is that you need, for a given graph, you need to be able to use this graph, but also the other one, which had only two atoms. So because you need to be able to take variable size inputs into your model, at some point you will need to do pooling, what is called pooling, either by summing all the vectors for this atom with all the vectors for this atom, or averaging, or maybe you can use some very sophisticated steps with the recurrent neural network that will allow to take many inputs and put them into a single output. There are a lot of methods that fall under the umbrella set to set in that respect, but yeah, basically there is a pooling step where you reduce this collection of vectors that corresponds to your graph to a single vector, and at the end you can simply pass that through another neural network to get the prediction. So you can see what I was talking about when I said there is an intermediate step here, which is that one just after the pooling, where whatever property you are seeking with this neural network, you will probably get a very good vector space where every material will correspond to a given position in that vector space. And this vector space will discriminate between the different properties of the materials. And then you can do a classical neural network fit, a simple neural network fit to get a regression on the given property you want. And you could train only that part of the neural network to get very good properties starting from an already trained neural network. So this specific neural network that I introduced is called CGCNN, and the particular neural networks that it uses for the message passing part or the convolutional part is this equation here. So there is like a concatenation of every node with every graph, with every edge vectors of your graph, and then you pass it through a transformation and so on. So let's not go into the details. CGCNN stands for Crystal Graph Convolution Neural Network. And then there are a full zoo of those models. So for example, SNET, we take the positions and pass them into like a system to properly encode the distance between atoms in a 300-dimensional vector using like basis functions to express that thing. And then this will be used inside the convolution layer, and then there will be like skip connections that they call inside. And yeah, so now you see how the complexity of those models can grow very fast, but the basic building blocks are those which we visited in the talk. Then there is MagNet, which is another one. DimNet realized that if you didn't have the information about angles, you could not discriminate between 6 hexagon of atoms and 2 triangles, because those have the same number of neighbors at the same distance and so on. So they included angles in there, and they do an embedding for angles and an embedding for the distance, and they use that embeddings throughout a sequence of steps, and every interaction block in here is this whole big operations where you take one of the prepared embeddings and pass it through these operations that convolute with that other embedding, and yeah, so you see that like the model can become very sophisticated very fast. And it's not obvious at the moment that any of these models is a lot superior to the other. So within 2 or 3 years, we've seen like a lot of models, and I've only shown a few of them. And typically in papers, they have this criteria of what was the performance of a given model on the energy of formation, for example, compared to another model and compared to that one, and then they are happy because they get the best performance. But actually, if you take those models and you try to re-implement them yourself, maybe the performance you would get would be a little bit different. And one of the models, for example, CGCNN in Umar's work, was a little bit better in the end than MagNet, although the paper of MagNet claimed the opposite. So, and remember that we said if you're in the 0.1 electron volt per atom, it seems that you're good enough. And now we're a lot below that. Okay, so we're half into the precision that we needed. So those models like perform correctly according to that criteria. If you look at the band gap, it's a little bit the same thing. The error for CGCNN on our side was lower than what we got, and we outperformed for some reason. Maybe we didn't use the exact same data set. Maybe we used different loss functions. But yeah, so we outperformed both of those methods. So this is very interesting. Those are ongoing results on our side. We are making new models, trying the experiments, and trying to predict some properties. Specifically, we will be trying to predict the magnetization of materials soon, because we have a project with André-Marie with Institut Quantique on this. But yeah, this gives I think this gives the whole picture, and this brings me to my conclusion. We've seen that neural networks can be seen as a machine intuition, something to compute very fast, approximative results in order to like screen a large data set or something like this. And then I showed you how materials can be found on the internet like as chunks of numbers, and which neural networks are used right now to crunch those numbers and get properties. So thank you very much for your attention, and I will now take questions.
Okay, so there was a question in the chat that I will ask you. So Simon Bertrand asks, what do you want to optimize? Is it just the prediction of the band gap, or are there other parameters at the same time, or maybe it depends on the...
Yeah, this is an excellent question. When you train on the formation energy, you want to optimize for example, the mean absolute error of the formation energy. So you simply take the difference between the target and your prediction. When you want to predict the band gap, there will be an overrepresentation of zero band gap, because there are insulators and metals. So there are ways to first do a classification step, or first predict a class with your neural network, and then use that class to mask the prediction that you would actually give for the gap, and that way try to optimize the neural network with a signal coming from an error with this composite prediction. And for other properties, there would be other ways to predict. And for each of those properties, if you train the neural network on that property only, you will get very poor results on another property. So you could decide to try to train the neural network on many properties at the same time. This is easy because the neural network doesn't have to give you a single output. It could give you a vector, and you could use the various components of that vector as multiple targets. And when you do that, you usually lose accuracy on each one of those targets. This is not true for all neural networks, but with graph neural networks, it seems to be the case. And because of that, our experience was it's better to seek a single target at a time. So yeah, there are many possibilities there too.
So Simon, is that a good answer to your question? Okay, yeah, he says yes, okay. So I think David has his hand raised, so go ahead, David.
Yes, okay. Maybe to question which is not relevant, but you have a unique graph coming out of a unit cell, provided you know what neighbor means, right?
Yeah.
Because there could be some ambiguity in what a neighbor is, depending on distance and so on. But I mean, I suppose this is not reversible, is it? I mean, if you have the graph, can you find the unit cell?
Oh, this is a great question. I would guess no. I haven't given much thought to this. It seems obvious that no, indeed, if you agree with me. And yeah, this is part of the problem of. But if you have all the distance and all the angles for all the edges of your graph, maybe then you can reproduce your unit cell.
Yeah, okay. It's not important when you go in one direction anyway. Another question, if I may, but that refers to an earlier part of the talk, is about the database with the Hubbard U. You know, the two bumps in your distribution of formation energy, I think, right?
Yeah.
So, okay, I'm amazed at the number of compounds where you have that Hubbard U information. It's like half of the total or something, roughly. So why is that? Is that just, because I thought, that strongly correlated materials were sort of a small subset. Is it because of a biased interest, or is it something that is more a picture of the distribution of real materials out there?
Yeah, this is a great question. We are investigating this currently because we discovered that not so long ago. And I think the answer is that whenever they use or whenever they try to model perovskite, they end up having a F shell, and in those cases they use DFT plus U. Because when I mean Hubbard U, I mean DFT plus U.
DFT plus U, yeah. Okay.
And yeah, Chloe would be a lot better than me to answer that question. If Chloe wants to jump in and make a comment, it would be great. Otherwise, this is a good question. This is a bias that we'll have to look into. For sure.
Okay. Thank you.
Okay. So there's also Siku who has his hand raised, so maybe you can jump in.
Good.
Yeah. So I just have a comment regarding the first question that David asked. So it is true that there is a correspondence from unit cell structure to graph. So from one unit cell structure, you get one graph only, and that from one graph, you can't recover the unit cell. So that's the problem that DIMNet, the model Simon mentioned that includes the angles, tried to circumvent. I'm not sure that if it, wholly solved these problems, but another thing is for sure is that there is another possibility than using graphs. You could just have a list of atoms and include in that list the atomic number of the atom and the position of the atom. The problem with doing that is that there are symmetries in the problem that are not considered by using this approach. So by encoding the position of each atom into the data structure, you're not exploiting the symmetry of the problem, because you could just, for example, translate all the position by a given vector or something like that, or do a rotation on every vector, and you'd be supposed to get exactly the same output at the end of the neural network, but it would not be the case because of this data structure. So the whole problem is to try to come up with some data structure or mathematical object that encodes the unit cell structure perfectly, while at the same time being able to leverage the whole symmetry of the problem. So yeah.
Extremely relevant comment. Thank you, Uma. Maybe it's a good time also to say that Uma will be beginning a PhD at McGill, kind of on that subject, like using invariant neural network for problems such as crystals. So yeah, that's why he has a relevant comment as this one for this subject.
Okay, so maybe one last question. I see Maxime has raised his hand too, so.
Yes, a very basic question. I would like to hear you about, you're showing pretty complex model, pretty complex neural network, try to modelize these crystals. Can you compare the cost of just doing the DFT and calculating the properties that you're looking for compared to just using these user model?
Yeah, good question. Okay, so when we train a neural network like this one, doing one epoch, for example, training this model by seeing and predicting the properties for every materials, takes on the order of a few seconds, maybe a few minutes in the worst case scenarios. So, and this means that you predict the property for 50,000 materials. So it is extremely fast compared to DFT, which requires a lot more time to end the computations. However, in DFT, you have a lot more information at the end. You have the positions of every atom. So you can get a lot more from a DFT calculations. So that's why at the beginning I was saying neural networks are very flexible, because you can like reduce the size of the neural network to get something even faster. But out of the box, they are always, even when they are very, very complex, they have to be very fast, because you have to train them on thousands and thousands of samples. And it is the training that is very long. And once the neural network is trained, it's almost instantaneous to get a prediction.
All right, so I don't see any more hands raised. So thank you everyone for being here for Simon's talk. And yeah, see you next week.
Thank you.
Thank you, Simon.
Salut Alex.
Je comprends pas trop pourquoi je me suis remonté en plein écran. C'est un peu surprenant.
Je partageais mon écran, puis c'est toi qui étais là.
OK.